I'm Drew Myler. I'm in Will Hyde's second period class.
Hi, my name's Carter Wells. I'm in Easton's third period class. We are professional recreational D-League softball players.
And you're going to learn some physics today. Yay!
A projectile is an object that is only being acted on by the force of gravity. For example, this softball will be a projectile. This softball was a projectile because when it left my hand, the only force acting on it was gravity itself.
It was another example of a projectile after I smashed the living daylights out of it, and when it left, the only force on it was indeed gravity. An object is in free fall when the only force acting on it is gravity. So I'm going to show you an example, and then I'll explain it in a second. You ready, Carter?
Yeah!
After I hit the ball, the only force acting on it was gravity, so by definition, it was in free fall.
A free body diagram is a diagram where you draw an object and the forces acting on it. This is an example of a free body diagram because the object is in free fall, so the only force acting on it is the force of gravity. That's why we drew an arrow facing directly down. Force of gravity is equal to mass times acceleration due to gravity, which is why we wrote mg.
Accuracy is the measurement of how close something is to its intended target. Here's an example. Ball game! This was an example of accuracy because the intended target was the middle of Carter's glove. And just like right now, he didn't even have to move. Precision is the closeness of two or more objects between each other. Here's an example. That was an example of precision because all of the balls went over Carter's head at relatively the same spot.
Drew's going to pitch the ball to Alex. Alex will then bunt the ball back to Drew. Drew will measure the distance between Alex bunting it and Drew fielding it using the handy-dandy tape measure. Now Drew will throw the ball to Delaney to throw out Alex. We will then measure the distance between Drew fielding it and throwing it, and Delaney catching it. This is where Drew fielded the ball. He threw it 48 feet, and Delaney caught it. You're out. Now we will calculate the displacement, which is where the ball was hit and where Delaney caught the ball at the end. The displacement was 60 feet.
Distance is a scalar quantity that refers to how much ground an object has covered, while displacement is a vector quantity that is the object's overall change in position. The distance it traveled was 62 feet because it traveled 14 feet plus 48 feet in a different direction, which is 62. The displacement is 60 feet towards first base because it started at home plate and ended at first base, and you just measure the distance from the start point and the end point, which is 60.
Relative motion is how the motion appears to be depending on your point of view. Here's an example. Here's my perspective.
Here's the camera's perspective.
From my perspective, it looked like there was no horizontal velocity. But from the camera's perspective, it looked like there was a horizontal velocity. The difference between speed and velocity is speed is a scalar quantity that measures distance over time, whereas velocity is a vector quantity that measures displacement over time. Here's an example.
All right, so Carter's going to hit the ball, and I'm going to time the amount of time it takes for him to run from home all the way around the bases back to home. So slow. He's so slow. Look at him. What a slow poke. Oh my goodness, he's so slow. So you're doing great, sweetie. You got this. Take your time.
In order to find our speed, we need to find our total distance over time. As we know from earlier, our distance between home and first base is 60 feet, and that'll be the same between all 4 bases because it is a baseball field and it's a diamond. So 60 feet is actually equal to 18.3 meters, so we multiply that by 4 to get our total distance of 73.2. Our time was recorded as 14.7, so we divide our distance, 73.2, divided by 14.7 to get 4.98 meters per second, and that is our speed for Carter rounding the bases. Our velocity, however, is far different. Since it's our displacement over time, we started and ended at the same spot, so our displacement is actually 0. And we divide that by our time, 14.7 still, and that gives us a velocity of 0 meters per second around all 4 bases.
Alright, Newton's first law states that an object at equilibrium will stay at equilibrium unless there is a net force. Here's an example of Newton's first law. So the ball would have kept rolling, but there was a frictional force in the opposing direction and it slowed it to a stop. So the ball was in motion and then it became at rest because there was a net force acting on it.
Newton's second law states that acceleration is equal to the net force over the mass.
Alright, so Carter and I are sitting 9 feet and 10.11 inches apart from each other, which is exactly 3 meters. And so I'm going to throw the ball to Carter, and I'm gonna time how long it takes for it to leave my hand and then touch his. And we're going to use that information to find the acceleration and then find the net force.
So using Newton's second law, we can find out the net force between me and Drew. We found out after weighing the softball that it weighs 1.25 pounds, which is 0.567 kilograms. Also, we know that the distance between me and Drew was 3 meters, and the time it took for the ball to get to me from Drew was 0.54 seconds. So we can use that to find our velocity. So we divide 3 by 0.54 and get 5.56 meters per second. Then we plug that into an equation, v squared equals v squared naught plus 2 acceleration delta x to get our acceleration. After moving it around, we can get that v squared over 2 times delta x is equal to your acceleration. Plugging in our numbers, 5.56 squared, which was our found acceleration, over 2 times our delta x, which is 3 meters, we find that our acceleration is 5.15 meters per second squared. Then we can finally plug that into Newton's second law's equation. The net force is equal to mass times acceleration. So our net force is equal to 0.567, which was our mass that we found, times 5.15, which was the acceleration that we found, to get our net force between the throw of Drew to me, equaling 2.92 newtons.
Newton's third law states that for every action, there is an equal and opposite reaction. Here's an example.
I'm sticky! Hey guys, Drew here. I just find it fascinating that Newton's third law can be used for more than just physics. For example, this is how I make guacamole.
Don't you just hate melons that can't get married? For example, this cantaloupe.
Hey guys, Drew again. I just wanted to share with you, I have another recipe for pumpkin pie.
I also have a really good recipe for apple pie. That was an example of Newton's third law because when we hit the fruit with our bats exerted a force on the fruit, and the fruits also exerted a force back on our bats.
And that's why our bats didn't maintain a constant velocity all the way around. So we hope you learned a thing or two today about physics and also how good we are at hitting dingers, and also about our passion for professional recreational D-League softball.
My name's Carter. That's Drew. We're part of the ADT WASP. We hope you enjoyed.
Physics.
Ah! What the heck?